All right. Uh, someone let me know they can hear me.
I can hear you.
Okay, we're good to go. So I'm married. I just found out Boris Johnson has COVID. I don't understand how this works. So I like his hair, so I hope he survives. Good luck. I'm also a citizen of Britain, so in theory, I should care about this. So Wake County is going into shelter in place at 5 p.m. today, but I found out that faculty who have to teach are exempt. That would include me. So I'm just going to keep coming in and teaching from here until somebody tells me I can or tases me or puts me in jail or something like that. I talked to my dry cleaner. They're exempt. Hardware stores are exempt, I believe, grocery stores, gas stations. In fact, I think the only people I've heard that aren't exempt so far are hairdressers. So I don't know what's up with that, but anyway. So that shouldn't make any disruptions to the class schedule. And I've put the next 3 classes Zoom meeting information into the announcement section, so you should have received an email. If you didn't or you don't have it anymore, you can go to the Moodle webpage and the links are there for the Zoom meetings. And so I got a recommendation to set up the Zoom meetings so that you can actually see one another and or whoever's talking will take over the screen. I'll do that for next week. It's fairly straightforward to do. The ability to actually see anyone who's sharing video, I think you'll have to do at your end because that's part of your Zoom meeting control. And no Zoom bombing, please. You can't actually because I've turned off background image selection, but do you all know what Zoom bombing is? Nobody knows. Basically what was happening in classes was either people were being hacked or they were doing this themselves. We will assume they were not doing it themselves. But you can put pornographic images up as your background. So that's a no-no. And so I don't allow you to set your background image just to avoid that. So it was interesting because I was watching on the computer science email list, and so there was this massive conversation about this amongst the faculty. Blah, 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 blah. What can we do? How can we figure out who's doing it? Blah, 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 blah. And I was sort of like, oh. And so at some point I finally chimed in and said, you know, you can just turn it off, right? So there was silence for a while. I think people who like to talk were very angry at me. Then they just started yakking again, like I hadn't said anything. So whatever. Other things, I don't think there's anything else you all need to know. I'm trying to put YouTube videos up as quickly as I can. So the main sticking point is just the processing time required for Zoom to create the local version of the recording, and then YouTube has to create a standard def version when I'm uploading because I think that's the account that Stake gives us. And then they show up and they seem to be working. So I have 2 followers now. I went out and had a big drink after I found out about that. So it's awesome. Yeah, so there's that. Any questions about anything that I talked about last class before I start, or anything else for that matter?
I have one logistical question.
Sure.
So you said homework 4 is now optional,
Yep.
but homework 3 and homework 4 are also due on the same date.
Yep.
I was wondering, is there any way? I mean, this definitely sounds like maybe trying to take a little too much advantage of that, but is there a way to see what our grade for homework 3 would have been as a way to see if it's worth doing homework 4?
Yes.
I'm still going to do the assignment, to be clear, just for my own thing, but if I have a high enough grade, I probably just won't turn it in. Do you know what I mean?
Yeah, I gotcha. And that makes perfect sense. That's a good question. So what I can do is I can push homework 4's due date back into the exam schedule, but I have to be a little bit careful because the university has rules about For example, even me moving homework 3 into the dead week is sort of a no-no. I'm not in theory allowed to reschedule things into dead week that aren't already in the syllabus. So I'm perfectly happy to move homework 4's due date to say the day before the final or 2 days before the final or something like that, as long as nobody has a problem with that. So what I'll do is I'll send out an email to the class through the announcement saying, I plan to do this and this is why, because you want to see your homework 3 grade. It'll also give you more time to work on homework 4 if you want to. And if anyone objects, they can email me directly and say they object. And unfortunately, if I get any single objection, then I won't be able to do it. The alternative would be to push homework 3 back a couple of days, and then you would have only a couple of days, I guess, to figure it out. I don't know if that really seems useful or not. But definitely I can go with door number 1. I don't really see anyone complaining. The class we have is all pretty good. But that would be the option that I could start with. Does that sound reasonable?
Yeah, I think that sounds good to me.
Okay, so let me do that. I'll do it as soon as I get back to my office. And hopefully everybody's fine with it. And we can go ahead with that. So what I'm trying to do is I'm trying to set it up so that you can take advantage of assignment 4 if you want to. And so it's a good suggestion to push assignment 4 back as far as possible so you have enough time to think about it and decide whether you actually want to dedicate the effort or not, and see how assignment 4 goes before you decide. Remember though that if you submit assignment 4 and it's not great, you're just going to automatically default to 110% of your first 3 assignments average. So submitting assignment 4 will never decrease your grade. It can only increase it. I tried to set it up that way.
Yeah, I think it was mainly in the case of if your other homeworks were not doing well, then
Right.
Doing the 4th one is advantageous.
Right, and that was exactly the option I also wanted to give people if they wanted, because it's funny, like you take a homework away and you think naively, everyone will be happy, there's less work to do, but of course people who need that homework or want that homework to improve their grade are not happy. And so we're keeping that option open as well, yeah.
Cool, thanks.
Okay, great. Other questions? That was a good question actually, so. All right, so let us continue with B-trees. And so last class, I just talked to you about the basic algorithm. I told you there were 3 constraints or guarantees from a B-tree. So every node's going to be able to hold up to k-1 keys in k subtrees. That's actually the definition of an order k B-tree. Every node except the root is going to hold at least the ceiling of k over 2 minus 1 keys. So it's always going to be at least about half full. And all leaf nodes occur at the same depth in the tree. So that guarantees that the tree is going to be balanced. And then the keys in a node are stored in descending order. So once you get to a node and you start looking for a key, you can do something fast like binary search if the node is really big and it's too slow to do a sequential search. Okay, so now all I'm going to do is I'm going to go through the 3 operations of search, insertion, and deletion. And I'm actually going to go through them in that order because that's the order that makes most sense in terms of understanding how these things work. So B-tree search. It's very similar to a BST, which is nice. So the only difference is that rather than moving recursively left or right at each node if you don't find the key, we must perform a k-way search to see which subtree to probe, or possibly that the key we're looking for is in the node that we're at. And so the simple intuitive way to think about this is you get to a node, you start at the left, and you start looking for your key. And you keep looking until you get to some value in the node that's bigger than your key. So if that happens and you haven't found your key, you know your key doesn't exist because everything's in ascending order. Only bigger things are going to be farther down the node. So you know that the previous value of the node that you looked at was smaller than your key, and the current value is bigger. So you want to follow the subtree between those two values. Okay, and that's why we keep them in ascending order. And so this is the algorithm. So you pass in a target, a node, and the order of the tree so that we actually know how big the node is. We'll just set some counter here to 0. And we'll say, well, s is less than k minus 1. So while there are still potentially values in the node to look at, if the target equals the node at our current position, then we can return the node's ref. And the ref is assumed to be the offset in the data file where the data record for that given target exists. So we have successfully found what we're looking for. Otherwise, if the target is smaller than the node's key, then we want to break target less than node key. Ascending order. I think this should be greater than. I'm going to change this, but I'm going to have to keep thinking because normally when I do this, I find out, no, I was right in the first place. But anyway, I think that's true. Otherwise, we bump up to the next entry. Okay. So you can see what this part of the code is doing. It's saying, start at the first entry in the node, check to see if it's what we're looking for. If it is, we're done. If it's not, check to see if it's bigger than what we're looking for. If it is, then we've passed the point where what we're looking for could be in the node. So we need to get out and probe a subtree if it exists, or tell the user there's no such key. Otherwise, just move to the next entry because we're still at values less than what we're looking for. See if that's what we're looking for. If it's not, see if there's more entries that could be what we're looking for, and just keep doing that until we either fall out of the node because we end up walking past the end of the node, or we pass the point where we could have found our key.
Excuse me?
Yep.
Quick question.
Yep.
I might have missed it why you switched the less than to the greater than, but if it is in ascending order, wouldn't you want that to be a less than? Because
Keep
so
talking.
I'm just trying to think it through for a second. So
Yeah, so am I.
if node at S, let's just say it was like 2, 4, 6, 8, 10, you're trying to find
Right. You're right, it's less than
1.
Because we would want to make sure that
You keep going.
right. Right. So let's say target is like 3, and the current position has a value of 4 or 10. Let's say 10. So it's possible that we're at 3, we're looking for 10. It's possible that farther down the line we could find 10, right?
Yes.
So we want to move to the next value and look at that to see if that's what we're looking for.
Yes.
And so what break is going to do is it's going to pop us all the way out here. So I think it's only if we walk past the value that we could possibly find that we want to get out of the loop.
Because you're trying to keep on searching the node indexes until you find one that's too big. And as soon as you find one that's too big, you know you're going to be to the left of that.
I gotcha. Yeah, I think you're right. Yeah.
I think.
And that's why I said, like, when I changed it, like, this is probably going to be wrong. And I think it was wrong. So target is less than. well, let's try a little example. So we'll set the target to be 3, and we'll have the values of 1, 2, 5, 7. Okay. So we start here, and is 3 less than 1? It's not, right? But it's possible, like if I change this to say a 3, it's possible that I could find it later. So I say if target, which is 3, is less than node at 0.key, which is 1, then break. So I'm going to pop out, right? But I don't think I want to pop out yet. I don't want to pop out until the target is bigger than the value that I actually find. So I'll change this back to a 5. So we're currently looking here, and I would say, is this true? No. Is this true? This is true. Is this true? No, this is not true. You're right. Yep, we're good. It's confusing to me. But you're correct, and the code and the nodes are correct, and whatever I change is wrong. So anyway, having said all of that, this will pop out when one of two things happens. We either exhaust the values in the node, or we find the place. We find the value, we exhaust the values in the node, and we find the place where we have to drop down. Okay. Now, one of the things I haven't talked about here is that the node doesn't necessarily need to be full. So there, in theory, is some check here making sure that there is another value to look at, but I haven't put that in here. So. Okay, so let us continue. So what we do now is we say if node s dot subtree isn't null, then we return search B tree target node at s dot subtree k, else we return a -1 to tell you that there is no such key in the tree. So what's happening here is that you're actually just doing a recursive search into the subtree for the same value. And if the subtree doesn't exist to search in, then you know that no such value exists in the tree. And so you return all the way up the recursion chain a -1 to tell the caller that key doesn't exist. Okay? So like I said, the code is very similar to the code for a BSP.
Dr. Healy,
Yep.
could you confirm that the subtree array is has a size that's 1 greater than the E array?
Yes, so the subtree array is going to be size k, and that's why we do a k-1 here.
Mm-hmm.
Yeah.
And then the S++ at the end is to get to the very last reference?
That's right, so you would get to S++, you would pop out, so now S would be k-1, right? And then you would be searching k-1, because we're 0 indexed, you would be searching the very last subtree pointer in the node.
Okay, thank you.
Yeah. So just to summarize up quickly what I said, this blocks through keys in a node, looking for a target key. it found the offset, or we call it the ref, to its data record location in the data file is returned. And if the key is not in the node, we recursively search the appropriate subtree. And we continue until the key is found or no subtree exists, which is a failed search. And so we initiate with a call to search the B tree, and we give it the root node, the target, the root, the number of values in the root, and it runs in order log k to the n time. Okay, and like I said, it's that massive k value that gives us the very quick performance that we want, because we have really wide nodes, and so that's in some sense exponentially increasing the amount of information at every level of the tree. So searching easy. Any questions about that? Okay. And so we have to show that maintenance also runs in order log to the k of n, or something akin to that. So let's look at insertion first. So this is more complicated than a BST. Not surprisingly. With BSTs, you just block down until you find an empty leaf and insert. If you're using one of these self-correcting BSTs, on insertion, you actually walk back up the insertion path and look at different lengths and possibly do rotations of the BST in order to correct for out of balance situations. Okay. Here, so I'll say, as with BST, you first search to find where you want to insert the key, right? So you remember with BST, we actually run a search first, and that gives us this empty subtree to insert into. With this algorithm, we're also going to do a search, but when we see an empty subtree, we're going to actually back up to the node that reference that empty subtree, and that's the node that we're going to want to insert into. Okay. The other thing is that B tree insertion must promote a value if a node overflows. Okay. And so let me first just give you the pseudocode for how this works. So first you search to determine which leaf will hold the new key. Okay. and that searching is exactly the same as the search B-tree algorithm we showed, except that you're going to want to return not a -1, but you're going to want to return a node that actually should hold the key value. And that would be that you recognize we wanted to insert it into an empty subtree. And remember, we build bottom up, not top down, so we wouldn't add an empty subtree we wouldn't add a new subtree with one node to the bottom. We would actually stick it in the node that pointed to that empty subtree in the proper position for ascending search. And so if the leaf has space available, we insert the key in ascending order, and then we stop because we're done. All right. Now, otherwise, we split the leaf node's keys into two parts, and we promote the median to the parent, along with the references to these two parts that we've created. One will be, we're actually only creating one new node. So one node we actually already have, so we keep the first half of the values, or whatever you want, the last half. Create a new node, stick the other half of the values in there. And then when we promote up, we give it the actual address of that new node, because it's going to need it when it goes to do the insertion in its parent. And then fourth, if the parent node is full, so it's possible that we can either promote up and we have space in the parent to hold the value that we promoted, or it's full, so then we would do exactly the same thing. We would split it into two pieces, get the median, promote it up, and so on. We recursively split and promote. And lastly, if the promotion is made to a full root node, we split and create a new root node holding only the promoted key. Okay, and that's that slight variation to the constraint. All nodes are at least half full except for the root node. And this is why. It's because the root node is always going to start out as having only one value in it. And then it's going to build up over time, either as you insert into it when you create the tree, or as you split and promote up to it as the tree gets bigger. Okay? So I'm going to show an example of inserting into an order 4 B tree. And before I do that, are there any questions about this strategy?
I have one question.
Yep.
I think in the examples we were showing last lecture, you would insert the key first, which would make the array overfull, and then you would split based off of that.
Yep.
In this case, do you wait to insert until you finished all the promotions and then insert?
So actually, you will insert, and then you will take that set of nodes, which is going to have k values, or sorry, the set of keys, which are going to be k of them, and you'll split them. You'll keep some in the existing node. You'll create a new node to put the other ones in, and then one of them you're going to promote up to the median. You're going to promote up to the parent. So you do actually, you can't do the insertion, I guess, in code explicitly because there's not enough space in the node, but you can create a temporary, or you can create a new node and move the values over to it and then promote up. So from a theoretical point of view, you are actually inserting before you do the split promotion.
Okay, cool. Thanks.
Yeah. Other questions?
Regarding number 5,
Yep.
does it mean that it's now possible that there could be more than one node that only has one element?
I don't think so. So the only way that you can actually get a node that has one element is if you have a root node that overflows. So it's going to split into two pieces, each of which is going to be about half full, and it's going to promote its median. And so you're still only going to have one node at that point that has less than half full set of keys in it. And I'll show you that when we go through the example, but I'm pretty sure, in fact, I know for a fact that for a B tree, it's only supposed to ever have one node, the root node, that could have less than half full set of keys.
Right. Okay. Thanks.
Yep. Other questions? All right, let's take a look at an example. And so if I had more board, I'd keep this, but I don't, so I'm going to erase it. But you'll see everything happening and remember the steps are going through. And I'm going to take a case that would be a complete dumpster fire for a BSD, just a basic BSD, which is, you know, the worst case is inserting already sorted or already reverse sorted. So we'll insert an already sorted set of values into the B tree and show how we still get a balanced tree. So consider inserting. I'm going to do A, B, C, D, E, F, G, H, I, J, K, L, M. In that order, into K equals 4, order 4 B tree. Now remember what that means. That means that every node will have up to 3 keys and up to 4 subchild pointers. Okay? So the first thing that happens is that A, B, C are inserted into the root node, right? Because they all fit. So we would have A, B, C. Okay? And then D overflows and splits the root. And because we have 4 values, I get to choose which one I'm going to promote. If we had an odd number of values at overflow, it would always be a middle one, but in this case, there's 2 choices. And so I'm always going to promote the right median, let's call it. So if I have A, B, C, D, B and C are the candidates, I'm always going to promote the right one, which is C. And so I'm going to promote C to a new root. So what you're going to have is you're going to have this A, B, C, and then there would be a D, right? I'll actually show you. So A, B, C, and then we add a D. So we overflow. So what we do is we promote C up to the new root. And this is what we have, okay? And remember that K is 4, so the ceiling of 4 over 2 minus 1, 4 over 2 minus 1 is 2 minus 1 is 1, ceiling is 1. So every node has to have at least 1 key in it, and it does. All right, so that's why D is allowed to have 1 key. So maybe I lied a little bit when I answered that question last time. Somebody asked me, is there ever a case where other nodes will have only 1 key? Yes, if your order is small enough, okay? So if we were a bigger order node, like if I was order 5, this couldn't happen. But for order 4, just because we're allowed to have ceiling K over 2 minus 1 nodes minimum in a node, keys in a node, then we could have 1 key, okay? So next we're going to insert E and F into D's node. So what happens is that we search and find we want E to go here, we search and we find we want F to go here, and they both fit. Right? And then G splits the leaf. So we would have a G on here, right? D, E, F, G, and remember that I always promote up the right of the 2 candidates. So in this case, I would be promoting F up. So we promote F on the split. So we're going to have C and F, AB, D, E, and G. All right? Because G is the value that we inserted that caused the split. So everything still looks good. A little nervous, but okay. So we insert H and I into G's node. Space there for them, so no problem. And then J splits the leaf. So we're going to promote, so if we had a J on here, we would promote I, because these are the two candidates, H and I. So we're going to promote I on the split. So we're going to now have a root of C, F, I, A, B, D, E, G, H, and then J is the value that we just inserted that caused the split. Okay? And then K and L, sorry, we insert K and L into J's node. And when we put in our final value M, so what happens here is that M splits the leaf. We promote, so we would have J, K, L, M. We promote L. All right. And let me just draw this out. So we would have C, F, I, L. So we're actually overflowing the root as well. All right. So L splits the root, promoting, well, if we have CFIL, I is going to get promoted because it's the right of the two candidates to a new root node. So we would actually have I, and then over here we would have C and F, and over here we would have L. Right? Because that was the root node was CFIL, and we promoted I. Let me pull up space in here. And then over here we've got AD, DE, GH, JK, and M, which is the value that we just added. Okay? So you can see that this is balanced. All the leaves occur at the same level in the tree. Every node except for the root node meets that requirement of ceiling of k over 2 minus 1. All right. And what were the other constraints? Go back now. Keys are in ascending order. All right. Does that make sense? Any questions about that? You feeling lucky? Nobody's feeling lucky. Yeah, it's a sign of the times, I guess. You want to try it? Oh, sorry, go ahead.
It makes sense.
Okay. Do you want to try it with k equals 5? I haven't done that, but we could try it and just see what happens. See, when no one says anything, I just do what I want to do. Even when people tell me no, I do what I want to do, I guess. So, I don't know what's going to happen, but I'm curious. And I'm just going to draw the tree. I'm not going to write out all that. But I do want to show you this just because I want to show you that, okay, this would be a situation where you're not allowed to have only one node in a non-root, only one key in a non-root node, because 5 over 2 is 2.5. Minus 1 is 1.5. Ceiling is 2. So you're going to have at least 2 values in every node except the root. So we would start out A, B, C, D, E, and then F, right? And so C is going to promote because
it's k equals 5, so you would promote at inserting
E. Good eye. See, this is what happens when I do shit where I don't know what I'm doing. Okay, that makes more sense. So C goes up. All right. And then G, H, I, right?
So we needed F.
Oh, did we miss F? FGH? FGH, sorry, my bad. So F goes up. Okay. IJK. So I goes up. LM. Oh, this is boring. Let's put some more values in here. NOPQRS. LMN. All right, so L goes up. And then we get OPQ. So what would happen is O would go up. But when O goes up, there's a problem, right? We have to split this. So I is going to go up. Right? And then we insert RS. So I should just mark out these are nodes. I guess I could be a little bit more clear about where these are going. So if you don't make mistakes like I did, the algorithm actually works. It's good. Yeah. Okay, any questions about that? I have to stand here because I have to have at least one picture of me standing here so that when I make my representative image for the video, there's a picture of me looking profound. There we go, that's how to do it. Any questions about this? Okay, the next thing that we would obviously look at is delete. Delete is yet again more complicated than insert or search. And I'm pretty sure for assignment 3, you don't have to do deletion for your B-tree implementation, only insert and search. Is that correct? Does anyone remember?
Yeah, that sounds right when I looked at it.
Yeah, I didn't ask you to do delete because, so the reason I didn't is because it's complicated only in the sense that there's a lot of housekeeping that you have to do when you're doing deletion, but really deletion and insertion are not that different in terms of how they manage values in nodes. They just do some rotations, basically. And so the fact of the matter is, and you probably understand this, if you're out in the job force or you're doing research like I am or something like that, and you need to use a B-tree, you don't normally write one from scratch. You normally use an existing library. And so my assumption is that if you ever wanted to use a B-tree, you could get an existing library for a B-tree or a B+ tree or a B* tree or whatever it is you're going to use, and it'll have a delete algorithm available to you. I do want you to understand how delete works, but I don't necessarily need you to implement it. I don't think that there's a lot of additional return on investment of doing that versus just the first two, which, to be honest, are going to be difficult enough to get working because trees with pointers and other things like that are always tricky to keep sorted. So that's why we're not asking for deletion. Which also means that at this point, you know everything you need to know to actually do the assignment. And so that's good. Are there any questions about this before we stop for the day? All right, any questions about anything in particular? All right, take care of yourselves. I don't know what shelter in place means for you all. Maybe you're already doing that. I mentioned social distancing didn't make a big difference in my life, so there was that. But I will be back here on Monday, and I will see you then. And when we're done, I'll be doing my office hour after that. And of course, contact me anytime if you have questions, and I'll be happy to answer them. I will go and send that email about assignment 4 pushback date as soon as I get back to my office. All right, anything before I stop? All right, thank you and enjoy your weekend.
Thanks, Dr. Goulart.
Thank you.